Welcome to NetSeminar. We're happy to have Arjun Singhvi from University of Wisconsin-Madison. We invited Arjun because his work kind of fits networking and recent themes we've been working on at Platform Lab. So let's hear what they have to say.
Thanks for the introduction. Good afternoon. I'm excited to talk about our work that examines the current granular computing implementations to essentially see if they are a good fit for network-intensive applications. This was joint work with Sujata, Yotam, my advisor Aditya, as well as Mark and Pontus. This work was presented at Hotnets last December. Over the last decade or so, we've seen a constant evolution of computing services. In the early days of computing, we had bare metal machines where it was all about the hardware and provisioning of the servers and things of that sort, where the application deployment was probably among one of the last stages in the entire deployment pipeline. Things did get better with virtual machines, where the whole idea was to virtualize the underlying hardware so that the user doesn't have to worry about it. However, as a user, you would still worry about the end operating system, right? With containers, even the underlying operating system was abstracted away, where as an end user, all you would now worry about would be the application as well as their dependencies. And I think finally we have granular serverless computing, which is the next in progression in this entire evolution, where we have another layer of abstraction where essentially the language runtime has been abstracted out. So the user just worries about the function code and nothing else. The main aim in this entire evolution, if you look at it, is essentially to decrease user management or user involvement in the management tasks so that a user can solely focus on the application logic. By this, what I essentially mean is that you do not want the user to spend a lot of time provisioning the servers, thinking about how to size the servers and things of that sort. All you want him to do is spend most of his time developing the core application logic, and the rest should be left to the service provider and things of that sort.
Question.
Yeah.
That sounds a lot like platform as a service, but I don't see that on your chart. What does that fit in? It seems to me I would put it in between containers and granular, but it seems to have the same thing that.
Yes, exactly. Yeah, so it is probably in between containers and granular serverless computing. So platform as a service would come in there, but
like Google App Engine,
yeah, or EC2 VMs and things of that sort, right? Yeah, and that's the right place to put it in. And the difference between those services and say granular serverless computing is that even when you have say EC2 VM with the auto scaling, load balancer and things of that sort, the user has to configure a number of parameters. So say you take the container auto scaling service which Amazon provides, right? So the user still has to configure when to scale up, when to scale down, and all those things. So the user still has to do those non-intuitive things. So it's one step ahead, but with serverless offerings, all of that is taken care by the cloud provider. You don't need to care about when to scale up, how to scale up, and things of that sort.
That sounds more like app engine. Where Google scales it automatically based on the number of users.
Yeah, sure, in that sense. But the other thing is also the way we program stuff in this thing, right? So that was what I was getting to, where traditionally what you would think of your application is essentially a monolithic piece of junk, right? But in this new computing paradigm, what happens is that you actually think of an application as a number of functions, so with or without dependencies. So here, the entire thinking of how a developer develops the application has changed, where he essentially thinks of the application as a number of functions which have been allocated resources independently. So you allocate resources based on each function's use. Right? So in some sense, this, yeah. Do you have a question? No. Okay. Yeah. So in some sense, this essentially enables to realize the dream of a microservices-oriented architecture. And if you again look back at this entire evolution of computing services, right, one question to probably ask is, what is the unit of scaling in these abstractions, right? So in the virtual machine, the scaling unit was the entire virtual machine, where you would actually replicate the entire VM, right? With containers, the scaling unit became an application where you would replicate the entire application. However, with granular serverless computing, the scaling unit is a function. So the entire deployment unit is a function. So that is the key difference, where you have two changes, right? The way you deploy things as well as the way you program stuff. So things have changed in those aspects. So at a high level, now let's look at the end-to-end control flow of a granular serverless platform. As an end user, what you would do is typically upload your function to the serverless platform. You would typically say configure the amount of memory you want, and most of the existing platforms configure the required resources by some internal algorithm which probably allocates a CPU proportional to the amount of memory you've configured as such. And apart from that, more importantly, what you would do is you would essentially register for an event-based trigger, and most of these serverless platforms have a wide variety of event-based triggers. Something as simple as an incoming HTTP request or a file being uploaded to a storage service which is maintained by the cloud provider. And then what happens is that the execution of your function is triggered when the event actually happens. And as a result, you just pay for the actual time when your function is running. So you don't pay when your VM is just say running without any incoming requests, right? And the other unique selling point of these serverless platforms is that they claim that they auto scale based on your incoming load. That is one of the key selling points because of which most of these platforms have been adopted, because the users now don't have to worry about the scaling up logic, scaling down logic, and things of that sort. Having looked at the control flow, now let's just look briefly at the basic building blocks of a typical serverless platform. It consists of a function scheduler, which, as the name suggests, schedules the function when a request comes in on a cluster of machines. So let's say when a request comes in, what the function scheduler would do is it launches a computational unit in the back end, and it runs the function there. However, a point to note is that as of today, most of these functions are stateless by definition. What I mean by this is that you cannot persist state locally in a function, and the reason for that is that there is no infrastructure affinity in the serverless platform. What I mean by having no infrastructure affinity is that, say you get one more request of the same function, the platform is not required to launch it at the same instance which it, say, serviced the previous request. It can launch it in any other part of the cluster. So then the data needs to be handled. So typically how things work in the serverless world is that your function interacts with other storage services which the cloud provides to externalize the entire state, so that when a new request comes in, the request first interacts with the storage, gets the required state, and does the execution. So that is the model of working as of today. And like I told previously, the claim to fame for these serverless platforms is that they scale infinitely and they scale based on load. And the fundamental reason why existing platforms are stateless is so that auto-scaling becomes extremely simple. Think of it, right? All the platforms need to do is that they need to launch as many copies of your function as your incoming rate, so as to auto-scale. So that's why they are currently stateless. In the past few years, there has been a lot of interest in granular serverless computing. It was started with Amazon way back in 2014, and now you have offerings from Google, Microsoft, and IBM. And over the last year or so, there has been a lot more interest with a lot of startups and open source projects also coming in. Folks at UW-Madison are also building their own serverless platform. And to actually lay emphasis on the fact that things are moving rapidly and everything is changing, since the Hotnet talk, which I gave in December, right, VMware has come up with its own open source serverless project called as Dispatch. And 2 days back, Cloudflare launched its own serverless platform, kind of serverless platform called as Workers. So things are moving rapidly in this domain. Prior research in the domain of serverless computing has looked at video processing applications, which is work out of Stanford, as well as running distributed applications such as MapReduce, pulse synchronous processing jobs, and things of that sort. And mostly in these two works, what they leverage from the serverless platform is something which was not intended from its original use case. The original use case of granular serverless platforms was to run something in response to an event for a small amount of time. But what these two works do is they essentially leverage the serverless computing platform as a source of compute. So they, for example, the distributed computing platform, if it needs to run a large-scale MapReduce job, it launches 1,000 functions in the backend to run the map phase and things like that. As a part of our work, we look at a third class of applications, which are typically network-intensive applications. By network-intensive applications, I mean packet processing applications, which are known as network functions. Before getting into why we choose network functions, let's briefly look at what are network functions for people who don't know it. For people who know it, it will probably be a quick recap. So network functions typically examine and perform sophisticated operations on packets and flows in order to ensure security, improve performance, and provide other networking-related functionality. Examples of these can be a firewall and intrusion detection system, a caching proxy, a load balancer, or something even as simple as a network address translator. Most of them lie in the critical path between the source and the destination. And needless to say, they should be capable of handling packet bursts and failures. Another point to note is that the typical deployment pattern of these network functions is in the form of chains. What I essentially mean by this is that once a packet leaves the source machine, it goes through a number of network functions before it reaches the destination machine. An example of a network function chain could be that your packet goes through a firewall, then it goes to the intrusion detection system for further inspection, and finally to the cache and the load balancer before it actually goes to the destination server. There are a lot of different network functions out there, and depending on what they do, the internal state which they maintain is completely different. This internal state maintained by a caching proxy is different from an IDS, and that's definitely going to be different from what a simple firewall or a NAT maintains. But it turns out that despite them maintaining different internal state, the way they create or update the state is common. They essentially think of state as being associated with a particular flow or a collection of flows. To give you an example, let's look at the state maintained by an IDS. More specifically, let's look at the state maintained by Bro, which is an popular open source intrusion detection system. Here, for every incoming TCP connection, essentially we maintain certain objects. We maintain a connection object as well as various protocol-specific objects like the TCP analyzer, the HTTP analyzer, which are organized in a hash table. And apart from this state, we also maintain per host connection counts, which essentially maintains the number of connections which were successful with a particular host. The key takeaway from this slide is that in the context of network functions, there are two classes of internal state. One is the per flow state, and the other is the cross flow state. In the per flow state, as the name suggests, only packets belonging to a particular flow can modify or change that state. Whereas in the cross flow state, packets belonging from different flows can actually update or modify that state. Traditionally, network functions are deployed in proprietary hardware boxes. However, in the last few years, there has been a trend of virtualizing these network functions, where the key idea is to replace these hardware boxes by virtualizing them and running them on commodity servers, with the main aim being to reduce costs. The other advantage that we get with virtualization is that now you can dynamically allocate NF instances based on your load. Right? And with SDN, you essentially use that to reroute traffic between these instances. So this combination of virtualization and SDN essentially lets you introduce new services also quite fast. Think of it prior to this mode of deployment, right? When you had proprietary hardware boxes, if you wanted to introduce something into the network, you would have to build your own hardware box, a proprietary hardware box, and then you would have to actually install it in the network. But with virtualization, all it boils down to is launching a new VM with the new logic. So coming back to the question as to why we chose network functions as our class of application, there are three primary reasons for doing so. Firstly, network functions are a demanding class of applications because they lie in the critical path between the source and destination. So the throughput and latency guarantees which network functions require are far more demanding than, say, the previous applications which have been considered, such as video processing and distributed computing applications like MapReduce. So as a part of this work, we want to actually run such demanding applications on top of existing granular serverless platforms and see if there is a bottleneck out there. Next, there is also a trend of pushing these network functions to the cloud with prior work such as Aplom, Embark, as well as AT&T's Domain 2.0 push, which is essentially trying to virtualize these network functions and push it to the cloud to get the benefits of cloud such as elasticity and things of that sort. And lastly, let's imagine if in the future, serverless granular computing becomes the de facto standard in way things run in the cloud, right? Say the programming paradigms becomes that. Then as a part of this work, what we want to do is essentially find out the flaws or the gaps which are missing in the existing serverless platforms so that we can influence the next generation of computing services. having understood why we chose network functions, let's briefly look at why is it challenging to run network functions on top of such serverless granular platforms. On one end, you have serverless computing where the computational units are typically short-lived. What I essentially mean by this is that as of today, most of these platforms restrict the amount of time for which a function can execute. So they have a maximum time limit. Let's take the example of AWS-Lambda. It lets you run a function for a max of 5 minutes, or Google lets you run it for 9 minutes, right? So they are typically short-lived. The functions are stateless by definition, as we discussed earlier, and the fundamental reason for this is so that the platforms can auto-scale easily. They have no support for efficient chaining as of today, and they provide no quality of service guarantees. Huh?
That sounds like an Achilles heel or something.
Yeah. And on the other hand, you have network functions which are typically long-lived. You might have flows which last more than the limit of the platform. They are typically stateful, where network functions maintain per flow as well as cross-flow state. They need efficient chaining. As stated earlier, the typical deployment model of these network functions is that you have a chain through which the entire packet flows before reaching the destination machine. So you need to have efficient chaining. And since they lie in the critical part, you need quality of service guarantees in terms of low latency and high throughput. So having looked at the mismatch, the natural question that now comes to our mind is what opportunities do these serverless platforms provide for us to run applications like this, right? Getting into that, there has been a long-standing vision of having a microservices-oriented NF architecture where the key idea is to have a framework which lets you scale independently, reuse components across network chains, where the key idea is that you want to reduce costs and you need flexibility. And on the other hand, you have serverless computing, which, if you think of it, provides you the building blocks for the same. It has the capability to scale based on load. It encourages developers to naturally think of their applications in terms of microservices or functions, and it also reduces the cost. For example, let's look at the hourly cost of running a 40 gigabit firewall, and if we run it on EC2 VMs, it would cost us around $8 per hour. And if we run the same thing on AWS Lambda, it would cost us less than $1 as of today. As part of this work, we essentially came up with two strawman architectures to run network functions on top of existing serverless platforms, where the key design question was, what is the granularity at which you want to launch the function or the Lambda, right? So you have the Lambda scheduler or the function scheduler, you have a cluster of machines, and the key design question is, when do you want to launch a function? A natural answer to this would be to launch it for every packet, which we call as the per packet approach, where the idea is that for every incoming packet, you would essentially launch a function or a Lambda in the backend that would process the packet and stop there. While this fits naturally into the current serverless platform, it has a couple of drawbacks. It is not viable in terms of cost. For an example, the 40 gigabit firewall in this approach would take us more than $4,000 to run as of today. And the main reason for this is that when you launch a function, these cloud providers charge you in two factors. They have a per request charge as well as the compute charge. And if you have a per packet approach, then what happens is that your request invocation cost tends to dominate the entire thing, because say you have millions of packets, then you have to pay for those millions of requests which are handled by the platform. However, I think a lot of emphasis should not be laid on cost because it is something artificial and things might change. I think the emphasis should be laid on performance. And even in that aspect, this approach is not viable because if you think of it, these functions are stateless by nature. So if you want to process a packet, it would have to access a remote store and then process the packet. So you have this additional latency of going to the remote store and then processing your packet, which inflates your per packet latency, which can be unacceptable.
Also, even the time to spin up a Lambda is really high, right?
Yes, the other thing also. So the other point is also the control plane latency, where one of the things is that you typically have to start up a Lambda or a container in the backend, and the time to actually start that up is also something which is non-trivial. These cloud service providers use tricks like keeping a container around so that you don't pay the entire charge of spinning up the entire container, but even there you have to unpause it, which also has some amount of latency. So even that is something which you can't avoid. The other granularity which we explored was the per flow granularity, where as before, you had the Lambda scheduler as well as the cluster of machines, but we introduced two new entities, the coordinator and the gateway. I will briefly now walk through the control flow so that the roles of these two entities becomes clear. So in this platform, if a packet belonging to a new flow enters the system, a notification is sent from the gateway to the coordinator. The coordinator in turn requests the Lambda scheduler to actually launch a function or a Lambda in the backend. The Lambda, which is actually running your network function code, is launched in the backend. It establishes a persistent connection with the gateway, and then the packet flows to the network function. It processes the packet, and then it's sent out of the entire system. Now, if a packet belonging to the same flow comes, it directly goes through the persistent connection which is maintained between the gateway and the Lambda for processing. It doesn't need to have to go through the entire control plane. So that overhead of going through the control plane is circumvented here.
Yeah. Yeah. So the Lambdas need to initiate the connection to the gateway, right?
Yes, as of today.
And if you want, and if you need to send to send the request another Lambda, how do you do that? If you have a chain of Lambdas.
Oh, if you have a chain of Lambdas, in AWS. Yeah. So the approach would be something similar to what XCamera, which came out of Stanford, took, right? So you essentially have a coordinator which will maintain persistent connections with all of these, and then it would go to the coordinator, and then it would go through to the next Lambda. So you'll essentially spawn, say it's a chain of 5 network functions. You'll have these 5 network functions running, and then you would pass it through. But there are issues with that.
So you need many extra hops.
Yes,
and that's latency.
Latency gets that. So in the current world, AWS has these restrictions, right, where you can't initiate a connection into a Lambda. So you can't have direct Lambda to Lambda connection. So in the current services which are provided by the cloud, there is a limitation. Yeah.
So maybe I didn't quite understand this right, but it looks like you have sort of a front end, which is a bunch of gateways. Are they statically provisioned, and how do you sort of scale that?
Yeah, so that's a good question. Yeah, so the idea is that gateways are essentially out of the entire serverless infrastructure, where it's typically, say, a VM, and we would scale them up and down based on our incoming traffic.
Because certainly you don't. You're not like spinning up a gateway per flow, right?
Yeah,
that would be very. I mean, that seems that that's a weak link into your system, right? Is the front end.
Yes, it is definitely the weak link. Yeah, like the part of this work was essentially try to do what we want to do on existing serverless platforms, and then come up with issues with them so that we can actually build a clean slate serverless platform. Like trying to do something like this on existing proprietary serverless platforms, the performance will not meet our requirements at all. Yeah.
And for the Lambdas, would you ever want to terminate it early if there are no incoming packets?
Yeah, so that's a good question. So there could be two approaches where if a flow ends, then you probably don't want to use that Lambda. Or the other smarter thing could be that you don't want to go to the control plane again, so you essentially divert one more flow into that. So it depends on what approach the coordinator or the gateway uses. There's again a question of, do you want to pack? You could probably also pack multiple flows into a Lambda and things like that, right? But that goes far more and more away from the entire serverless idea. Like even now, this approach is kind of going away from the serverless idea in some sense. Yeah.
Can you give me examples of what's the?
Yeah. Okay. Yeah. So my bad. Yeah. So typically a flow is identified by the standard phi tuple. So you essentially you identify a flow by its source IP address, destination IP address, source port, destination port, as well as the protocol. So you identify a unique flow in that sense, and then you route it to a particular Lambda. Was that your question?
So you said per flow invocation of Lambda, then you mean keep Lambda for indefinite time?
No, so again, it's kind of related to her question, where you could keep it for indefinite time, where indefinite in case of AWS Lambda is 5 minutes, and then you essentially pass more flows to it, right? So you could do that, but then you'll have to have more logic in the coordinator, and the disadvantage there is that your lambda might also be idle, right? Say a flow has ended and you don't have traffic. You're still keeping it until the 5 minutes. So the other approach which you could take is that if a flow is finished, I will just take it out.
And also if the lambda expires, you get some interval service, right? Yeah,
exactly. So the other effect which we need to handle is that what if a flow is longer than the 5 minutes interval or the 9-minute interval which the platform is providing us. So in that case, the coordinator would have to be responsible for migrating that flow and making sure that the state is also moved. Any more questions? Yeah, so typically here, if a new flow comes, again, it goes to the entire control plane, a lambda is launched. And like we briefly went into this, while there are a lot of drawbacks with this approach in the sense that it doesn't fit in with the entire serverless paradigm, an advantage of this platform is that it makes the state management easier. So initially at the beginning of the talk, we looked at the two kinds of state which the network function maintains, right? The per flow state as well as the cross flow state. So in this approach, what you could typically do is you could cache the per flow state at the lambda. So what happens is that your lambda doesn't need to access the remote store for every incoming packet. It just needs to access the remote store whenever it needs to update the cross flow state, which may not be on every single packet. Say if the cross flow state is something like the number of connections which are established in this serverless platform, it would just be at the beginning of a TCP connection when the same packet arrives, right? So the advantages of this approach are it's cost effective because this is the approach which would cost you less than $1 to run a 40-gigabit firewall. State management kind of becomes easier because you can cache the per flow state and you handle the cross flow state in the remote store. However, you need additional infrastructure to actually coordinate the launching of new lambda, something similar to what he pointed out, that the front end is actually the weak bit here, where you essentially have to put in a lot more logic to actually have the system up and running. And more importantly, you cannot natively leverage what the serverless platform is providing, right? The key point of serverless platforms is that they say that we take care of managing the servers. We will auto scale whenever we think it is the right thing to do, right? But in this world, what we are doing is that the coordinator is the one which is actually deciding when to actually launch a new service function or a new lambda. So it's not really using what the serverless platform is giving us. I will now present some key results from the AWS benchmarking study, which we did as a part of this work. And the purpose of this study was to understand the characteristics and performance of the system. Most of these systems have limited or they do not have a lot of documentation about, say, how a network is provisioned or how much bandwidth we get in and out of a lambda. And that becomes extremely crucial for running network-intensive applications. So the purpose of the study was to treat AWS Lambda as a black box and actually verify how a network is provisioned, how does it scale, what are the chaining overheads, and a lot more things. So we ran all the experiments within an AWS region. For our network function experiments, we had the EC2 VMs, which acted as the TCP sources and sinks. We measured the performance of 3 network functions, something as simple as a packet counter, and we then moved on to firewall and an intrusion detection system. To understand how AWS Lambda provisions network for a function, we ran a simple experiment wherein the VM acted as an iPerf server and the Lambda had a statically linked iPerf client library loaded into it. And when the Lambda is launched, it initiates a connection with the VM and traffic flows in both directions. We measured the throughput in both directions as a function of the amount of memory provisioned to the Lambda. If you remember at the beginning of the talk, I said as an end user, what you typically do is you upload your function, you configure the amount of memory, and then the service provisions other resources proportional to that. And there is no documentation out there that tells us how much network is provisioned. So we wanted to run an experiment and see how much bandwidth we can get, whether it makes sense also to run the per flow architecture, right? The per flow architecture would totally not make sense if, say, it just provided us, say, 20 Mbps, right? It would become not that useful. So we ran an experiment. The x-axis shows the amount of memory we configured, and the y-axis shows the bandwidth which we get in both directions. And the key takeaway here is that we get a bidirectional bandwidth of around 500 Mbps with some amount of variation. Having looked at how the bandwidth is allocated for a given VM Lambda pair, what we wanted to see was if we have, say, 5 such lambdas or functions running, do we get 5 into 500 Mbps of bandwidth through it? It seemed quite intuitive to us, and we felt that if the platform is claiming infinite scalability, then it would also scale the network as the requests increase. So we repeated the same experiment, with the only change being that instead of having 1 VM lambda pair, we varied the number of VM lambda pairs which we had. And we varied it, as the x-axis shows, we varied it from 1 to 8, and we measured the aggregate throughput that we got out of the entire setup. Where by entire setup, I essentially mean that if we had 2 lambdas, then we measured the amount of throughput that both those lambdas gave us. And ideally, what we would have expected is we would have expected a linear line where 2 lambdas would give us 1,000, 4 lambdas would give us 2,000 Mbps, and essentially that trend. But what we see is that it's not a linear trend, and the reason for this is, let's say, an interesting rate limiting approach which AWS Lambda adopts. From our initial investigations, what we found out was that if lambdas have the same IP, which probably means that they are being run within the same VM, then together they get a combined throughput of 500 Mbps. So it seemed to indicate that they are doing rate limiting not at the per lambda request level, they were doing rate limiting at a slightly lower level, at the IP level, which could probably correlate to the VMs on which these containers or functions are being launched. But because of the black box nature of AWS, we couldn't really pinpoint the exact cause for this. But as far as we can tell, it's because they are doing rate limiting based on the IP. And as a result of this, the key implication of this was that there are no per lambda network guarantees. So this whole thing of if I have 2 lambdas, I can pump in 1 gigabit of traffic didn't hold any longer. So as a result of this, we couldn't run our experiments at large scale. That was a bummer. Next, we also looked at AWS Lambda in the aspect of chaining because, as I've told a number of times, the key deployment pattern of network functions is in the form of chains, right? And at the time of when this work was being carried out, AWS Lambda was the only platform which had chaining support of lambdas. So we chose, and that was one of the primary reasons why we chose AWS Lambda as a candidate as opposed to, say, Microsoft Azure or Google. So AWS has this service known as step functions, which essentially lets you connect multiple lambdas where there's no direct connection. It still goes through the control plane. So you still have that overhead of actually going through the control plane. And what we did was we ran a simple experiment where we varied the chain length and we quantified the control plane overhead. On the x-axis, we have the chain length, and on the y-axis, we have the overhead. And as you can see here, the overhead is not really small. It starts with being 50 milliseconds, and then it goes up to 250, and finally over 550. So this essentially indicates that there is high chaining overhead, and the reason for this is that it typically goes to the control plane after it finishes executing each lambda. So for our use case of network functions, where typically the per packet processing time is in the order of microseconds, such an approach didn't make sense at all because the overhead is just way too high. Yeah.
Also, the overhead here is like the average overhead or the tail overhead? Is it the average overhead or the tail overhead?
This is the average.
Okay. Yeah. So the tail could be
even worse.
Yeah.
Yes. Yeah, and it's kind of hard to actually pinpoint where it's spending a lot of time here because, again, of the black box nature of
that's really disappointing. That kind of indicates that this microservices architecture is not going to work. Or, the granular approach. I mean, when your function call turns in, when every function call turns into this like 100+ millisecond latency RPC, that seems terrible, right?
Yeah, it seems terrible. It would just work for when, say, the functions are running in the order of minutes or something of that sort, where such an overhead is acceptable, like something like the video processing work where you had to launch 1,000 lambdas and they would run to, say, 5 minutes. Probably there, they don't really care about the container startup time or this control plane overhead.
But if you can hide the latency, but even so, if you think about pipelining, think about all these lengthy latency gaps between your pipeline stages. That basically you have to amortize this by having really long running stages. Right?
Yeah. Otherwise, it becomes untenable. And finally, we also looked at the performance of network functions in the per flow architecture, where we essentially had the source gateway, we had the network function running within a Lambda, and we had the sync gateway. We ran it for 3 network functions, and we got a mean throughput of around 350 megabits per second, a mean end-to-end per packet processing latency of under 4 milliseconds. No doubt these are modest results, right? Even these results are not acceptable in terms of latency. You would want to optimize it even more. But it gives us a hope as to what future serverless platforms may enable. Like doing these things on AWS Lambda is extremely hard. Like you don't have root permissions on Lambda, or debugging the entire platform is a pain. So these results are modest, but it gives us a hope as to what future generations of computing services may enable. So in conclusion, the serverless computing platforms are not yet perfect. They are continuously evolving, and we can see that by the number of open source projects or the new features which people are adding. Like AWS continuously adds language support, and recently it added support for Go. It might change the way it's provisioning networks. So things are changing a lot. And if we restrict ourselves to the packet processing application, which was the focus of the talk, we would need efficient in-network triggers. Let me give you a small example, right? So in the per packet approach, when we actually tried to run it on AWS Lambda, the end-to-end overhead which we observed was 25 milliseconds. So we weren't using the front-end HTTP gateway or something of that sort. We removed all other services. It was us using the AWS Lambda SDK and actually trying to make a request and get a response. And there was an overhead of 25 milliseconds, and that's unacceptable for low latency workloads. Say you want to run a function which lasts only for a couple of milliseconds, or say even 50 milliseconds, an overhead of 25 milliseconds seems to be an overkill. And this is with their SDK. Our experiment showed that if you use the Amazon's API gateway, which is their front-end HTTP endpoint, which most people use, what we observed was there was a lot of variability, because you have one more service now, right? It's no longer your serverless platform. You have your Amazon's API gateway, and you have your serverless infrastructure, and they have to talk with each other. And the results which we got was that the variation was too high. Sometimes we could drive say 200 requests per second, and then it dropped to 50 requests per second because of the variation in the API gateway. So we got rid of the API gateway, we did all our experiments, but even with that, the overhead which we observed was 25 milliseconds. We need efficient chaining support because the overhead is too high. And if you need something like the per flow approach, right? No doubt the per flow approach doesn't fit with the event-driven model of serverless computing, but it kind of is similar to what prior work like the distributed applications or the video processes did, right? Where they are essentially leveraging the entire serverless platform as just as a source of compute, nothing else. So in that case, the per flow approach makes sense, but even for that to be viable, you need to have bandwidth guarantees. And I think this is nothing fundamental, because a few of our experiments reveal that if we have the same amount of traffic being sent to their internal service, which is Amazon S3, there was no bandwidth limitation as such. But if we send it to our own VM, there is some amount of rate limiting which happens. So I think it's just a matter of time where they realize that there are use cases such as these also which can run on their system, and then potentially that artificial limit would be restricted. So in conclusion, I would essentially like to end up with a number of open questions which this investigative study opened up, right? How would you design a scalable remote storage service that meets our requirements of low latency and high throughput, which is extremely important? How would you give better fault tolerant support? So one thing is that currently the fault tolerance model which these platforms provide is extremely simple. The model is as follows: if a function fails, they would just run it again, and they would run it again and again until it completes, right? And this makes sense for idempotent operations, right? Think of something which is not idempotent, something like, say, a network function like a packet counter, which is updating the packet count, which is kept in the remote store, right? Where if you update it twice, then you are double counting. So you need to have a better fault tolerance model in terms of both function as well as state. More importantly, you need faster control plane decisions. By this, what I essentially mean is that the control plane latency typically consists of 2 bits, right? One is the actual control plane overhead of scheduling, deciding where to launch the function, and the other thing, as you pointed out, is actually how to start up the function. Can you make the entire container or Lambda creation extremely faster? So that is something which needs to be looked at. And there are many other concerns, right? Like as to how does security look in such a world? Does the attack surface increase, or does it improve, or can we do other smarter things? The key question that what I'm getting at is, how would you effectively support demanding stateful applications on top of existing granular serverless platforms? Like originally, these platforms were designed for stateless applications, or where it was not extremely low latency. But if you want to support demanding stateful applications, then we actually need to think as to how can we do this. So that's the key question which we want to target. So this, I would like to thank you for listening to me. I'm open for more questions. Yeah.
We have tested the network bandwidth provision for lambdas. Could you go back to the plot where you have like step function almost? Actually, the one before maybe. Oh, this one, yeah.
Yeah.
So in this case, are you thinking that like for example, when you go from 1 to 2 lambdas, they have the same IP, so they are placed on the same like physical server, so they share the like total of 500 megabits per second network?
Yes, I think they're placed within the same virtual machine, which is probably run in some. So that is my hypothesis. But a key point to note is that it's not always 2. If it was always 2, I could probably run something, right? I can run 100 lambdas and I can get bandwidth of 50 to 500. But it's non-deterministic. That's what I've seen. It sounds crazy, but it is that across runs, this can be like 4 lambdas get the same IP. And so that's the trend which I've observed.
I guess did you find any like correlations? Are you sure? Have you like observed that whenever they have the same IP, then they
yes, I have
share,
observed
and
that.
then if different IP, they can like you get more.
Yes, that's what I observed. But this was done quite some time back. It was done last summer. I don't know if they've changed it. Things changed a lot. Yeah.
I just wanted to say how much I like this work, and I would really commend NSDI for accepting your paper, because we really need more of this, which is like these negative results where like those of them like, oh yeah, we ran some simulations and it went up into the right and it's 5% better than what we had last year, which is probably in the noise in terms of experimental error, which is plus or minus 200%. So this is like, oh, we tried this out and it didn't work, and here's exactly why, and here are all the problems you need to fix, and here's an actual research agenda for fixing it. So I think it's really fantastic. So I really commend you. And I think you really sort of hit the nail on the head too, which is that these platforms have absolutely no quality of service guarantees.
Yeah.
And unless they, and if they can take however long they want to process everything, then you're building on quicksand. And if they can always change their terms of service or whatever, and also they don't give you any communication, like you said, communication bandwidth guarantees are the thing that's always bothered me about AWS is they can't do any network application because I might get a gigabit, I might get a kilobit. Who knows?
Yeah,
it's whatever. It depends on whatever Amazon. Plus, there's steal time. They can always take however long they want to run your service.
Yeah.
But it's really clear to me that there's this it would be a huge advantage to be actually able to provision these things in a consistent way that I really get a bandwidth guarantee, and also be able to orchestrate, say, SDN infrastructure. So one thing you might consider doing, I think, is try something on like Genie, where you have like a programmable SDN infrastructure, and so then you can, for example, you can do what I call network function elimination, which is that for simple things like firewalls and load balancers and lots of those sorts of things, you can implement those as control plane SDN applications. And for things that have to do packet munging, like encryption or video, video transcoding or those sorts of things, those can often be done with data plane SDN with things like P4. So like if you had a programmable infrastructure, which you do in something like Genie, you might be able to sort of point the direction of like where Amazon, Azure, like if they had this, how well could you do? And I think you could do really well.
Yes, I think,
And obviously, I'm a fan of Aditya as well, and obviously, he's a good SDN person to talk to, because I think he would think along the same lines.
Yeah,
that's what you do with it.
Completely agree.
Right?
Oh, yeah, sure.
I guess for the first open question you have like listed on the slide right now, what is the storage, like remote storage requirements for like the network functions here?
Yeah, so you need low latency, high throughput. That's kind of obvious, but it's extremely strict. There's something like RAM cloud, right? So one exercise could be to actually see if RAM cloud is enough. Like there was one work called a stateless NF, which essentially traditionally what happens is network functions, the compute, the entire logic and the state are together. But what stateless NF proposed is separate the state and the actual processing logic. They used RAM cloud for it, but what they didn't take into account was that you have cross-flow state. So you essentially what you need to do is, if there is state which two lambdas need to maintain, so you need efficient arbitration at the storage layer too, or at TNF instances. So that is also something which makes it unique. Like the requirements are similar to low latency and high throughput, but the low latency is extremely low, in the order of microseconds. So if the other open question is, apart from the storage, what I probably didn't mention is the network protocol. Is something something like TCP enough, or even is something like RDMA enough, or do you need something even more for these low latency things? So yeah, that's what I mean by that.
And for the remote storage, you're only storing the cross-flow information?
So again, it depends, right? Because in this talk, I didn't go into fault tolerance, right? I mentioned about fault tolerance here as state fault tolerance. So that's extremely crucial, because if your Lambda crashes, you need your state to be there. So if you put your per flow state in your Lambda, sure, you're getting the performance, but it's at the cost of fault tolerance, right? Because if that Lambda fails, you lose your state. So then the question becomes, how would you make it fault tolerant? A natural thing is that, oh, I'll put it in the remote storage, so it becomes fault tolerant, but then you have this additional latency, right? So that's an open question.
I think you sort of suggested a solution there, which is, and she did as well, which is basically you're just log the state to something fast, and that's persistent now, like RAM cloud or something, where you basically in parallel. Basically log the state to a backing source, you have a hot standby. That seems like a perfectly good solution to me. And especially if it's low latency, like Microsoft, like.
Yes. It seems an acceptable solution, but the other thing also which we have to keep in mind is that the end goal is to come up with a serverless platform which is essentially not going to be used specific for network functions, right? We don't want a platform which is NS specific. That was not the idea of this work. The idea of this work was to essentially make a case for building a new serverless platform so that it can support more generic applications. And if that is our thinking, then the question then becomes is, does it even make sense for having such a replication model where it's totally fine to do it? Then the question is, should AWS or should Google actually have that as a service which provides it? Like in the serverless world, do you want something like that? So yeah, it's an interesting bit as to where the assumption there is that we would need to have something more out there, or could there be something other where some other approach where the infrastructure providers don't really need to give us something. Can we do something smarter? So yeah, there are two sides to it.
It depends on the application too, as like with network applications, often it's okay to drop a packet.
Yes, exactly, because it would think as the network has dropped the packet.
And so in that case, you sort of want the fault tolerance. You want the opposite of fault tolerance. You want it to just get out of the way and do nothing.
Yeah, in some sense, yes. Yeah.
Right. So just one other question for you, which is that big problem we've seen is these distributed denial of service attacks, where you have what appears to be zillions of legitimate clients, where you can't differentiate between the malicious and the legitimate. Do you have any thoughts on? And you have the sort of bottleneck of your front end, which is these VMs. But do you have any thoughts on how you would mitigate like kind of a distributed denial of service attack against this sort of thing?
Yeah, I think it kind of relates to this question of security which I brought up. Right? It's totally unclear as to how secure this entire new paradigm is, right? Because before serverless, what was it? You just had HTTP traffic and things of that sort. So you have standard techniques for that, like a web application firewall or the front end, which actually analyzes HTTP traffic, and it is capable of actually determining, hey, this is probably malicious and things of that sort, right? But with serverless computing, the attack surface is way larger, right? Because the event sources are so many. It's not only HTTP. It can be something as simple as an incoming SMS message or something which has a JSON payload. So I think with security, there are a lot of open challenges here. I think security needs to be taught through totally different angles. And again, there are two sides to it. Do you put on the cloud provider's hat and think of what services I provide? Or do you think of a user of this serverless platform and then you see how can you make yourself secure? So I think, that's again an interesting area to pursue, the whole security aspect in this.
But certainly there's this if you have something that scales out monetarily, based
Exactly.
on functions, then those functions could be spammed, and then that could be a big problem.
Big problem too. Yeah, yeah. Like if we use something like say the API gateway as the front end, and then Amazon has this service called as AWS Shield, so it has this DDoS detection or protection care where it says that if we think you have a DDoS attack, we will pay back the money. So that's there just with the API gateway, which is HTTP based. But for the other things, I'm unaware. Probably look it up.
Okay, thank you very much.
Thank you.